Okay, so we're going to get rolling on skill 3, the quotient rule, as I scroll to the bottom of my document and jump to a whole different page. There we go. Okay. What we have here is basically the quotient rule is ready-made for rational functions. So when you have a function with x on top and a function with x on the bottom, that's when this rule is going to apply. Where f and g are both differentiable, then the formula is f primed of x, g of x, minus g primed of x times f of x. So similar to product rule, except this is now a minus instead of a plus. That's why I told you to memorize the product rule in this order. The first thing's derivative first, and then you do the mixy-matchy. So it's not just that, it's then over g of x to the power of 2. So that's the rule. I'll show you an example where we use the rule, and then I'll prove that this rule in fact does actually work. So for this one is a quotient rule. H primed of x is going to be using kind of the short form f prime g minus g primed f over g squared. I'm going to go off to the side, f and f primed, g and g prime. So f is x minus 1, f primed is then 1. G is this to the power of 4. Chain rule says the 4 comes down, becomes a 3, inside stays put, and then we'll multiply after by the derivative of the inside, like so. And then I will write it all out. F prime g, so just 1 times g, so I'll just do 2x cubed plus 3x to the power of 4 minus g primed f, so the 4 blah to the 3 times this times f, which is x minus 1, all over g to the power of 2. So we've got x cubed plus 3x to the power of 4. If I square that, that's power on a power. You multiply the exponents. It's going to become 8. So there we go. So there's your kind of first line only. If I ever had to do anything with this derivative, I'd start by common factoring. So I'd common factor out the 2x cubed plus 3x to the power of 3 first, because there's 3 of them there and 4 of them in the first term. I'd common factor that out, and then eventually that would cancel and make the bottom exponent 5 instead of 8. So that's where I'd start, and then I'd kind of see what's left and probably start expanding the rest of the top. But that's, if I had to simplify it, that's where I would start, is definitely look for common factors in these types of questions. So I decided to show you how the formula works first before I show you the proof of it, because often the proof confuses people how to use the formula a bit. So I just want to show you now the proof of it. So we have h of x equals this. And so how the proof of this works is I don't have to go to first principles, because I have a product rule and a chain rule. The quotient rule you can prove using these two rules we already know. I can turn a quotient into a product, so I'll make it f of x times g of x to the negative 1. And then I can use the product rule, f prime g, g primed f. So f primed times g, and g isn't just g, it's g to the minus 1, plus g primed f. So g primed is going to be, then minus 1 is going to come down. We're going to get the inside to the negative 2, and then the chain rule says multiply by the derivative of the inside. So something like that. G prime times f. So bit confusing, so that's the product rule, but my second function, instead of just being g, is g to the minus 1. And then from there you get f primed of x over g of x. If I bring that negative exponent back down, I'm going to get minus, because of this minus, g primed of x, f of x over g of x squared. And then you can see to make it a single fraction, I'm going to multiply top and bottom of this fraction by g of x to give myself the common denominator. And we have our formula. So there's the proof of the quotient rule. And so this technique totally works. Like if you didn't want to learn the quotient rule, you could get by and just change every quotient into a product with this -1 exponent. The issue is your first line then looks messy compared to there's sort of these lines of simplification to get to this sort of more nice looking formula. So when I was in university, we had to memorize the formulas, and I thought I was being like quite clever. And I'm like, well, I'm not going to bother memorizing the quotient rule. It's got a minus in there. I might forget that backwards, and then I'll get the wrong answer. So I'll just memorize the product rule. The product rule is a plus. So I'm not going to screw that up. It's just FG and just mix and match the derivatives. But really, this formula here is not much more to memorize than the product rule. So f prime g minus g prime f, just remember the first derivative first, and then it's mixy matchy, it's got a minus, and then over g squared. Really, once you have that, then if you can memorize this, the quotient rule sort of starts out way more simplified than if you change it to a product and work with the negative exponents. So if you can use the quotient rule, you'll end up with a statement that's much closer to what you need if you ever had to do something with the derivative. So it's definitely, I was being foolish in university when I thought that. Looking back now, definitely worth it to remember this rule as well. So here's 4 examples here. So see if you can break these down into their parts using that quotient rule. So you can pause the video here, and then I'll go through them after you're done. So here we go. So this first function, f is the top, is x cubed, f primed is that, g is the bottom, g primed, you need the chain rule, and the derivative of what's inside is just 1. And then f prime g minus g primed f minus 1 to the 4, f is x cubed, all over g squared, which is going to be to the power of 10 now. So there's the first one. So here f is sine of thing. Derivative of sine is cos, and then chain rule says multiply by the derivative of the inside after the fact. G is easy peasy. And then putting those pieces together. So f prime g minus g primed f. So f prime 4 cos 4x plus 3 times g, which is 2x squared plus 2, already out of room. So I'll just erase this just so I have room to write out my answers. Minus g primed, f prime g, g primed f, all over g of x squared. All right, so there's our first 2 examples here. The third one just says y equals tan, and that's my hint that now that we know the quotient rule, we can actually get a nice formula for the derivative of tan because we know, so we won't have to go to, we don't have to go to first principles, we don't have to look up weird trig identities or anything like that. We know tan is sine over cos. So f is sine of x, f primed is cos of x then. G is cos of x, g primed is minus sine of x. And we will jump right to it. F primed cos of x times g cos of x minus g primed minus sine of x f sine of x all over g squared, so cos squared of x. And then I am going to simplify this one because we're going to want to use this as our formula for tan. So what it turns into is cos squared. The two minuses make a plus. Sine squared over cos squared. And then your favorite trig identities on top, sine squared plus cos squared is 1. So you get 1 plus 1 over cos squared, which that's a nice enough formula, but typically the way you write that is the secant squared of x. So 1 over cos squared is secant squared of x. So there's your derivative of tan. You can add that to your formula sheet. So now every time we see tan, we can write its derivative as secant squared. Oh, like this one. So here, derivative of tan is secant squared. The the chain rule says leave the inside in there, and then multiply by the derivative of the inside. And the derivative of the inside is a quotient rule. It's x over x minus 4. So I can write out f primed is just 1, g is x minus 4, g primed is just 1. Then writing out the formula, or sorry, putting the pieces together, f prime times g, so 1 times x minus 4, minus g primed 1 times f is that, all over g of x squared, x minus 4 squared. And that's good enough for a first line. Only for this one, obviously the top would simplify to just negative 4 if you wanted to simplify the top of that fraction. Would be a good start. Okay, so those are those examples. I'll get rid of my aggressive circle so that I can read the next example. So here's one where we're actually going to want to do something with the derivative. So we're going to want to simplify the derivative because we want to prove that the derivative, or sorry, that function never decreases. So what that would mean is we're going to take the derivative and show that that derivative can't be negative. So we begin. I encourage you to pause the video before my solution and try and get to the answer yourself. So see if you can get this derivative and convince me that it's never going to be negative. All right. F primed 5 times g x plus 2 minus g primed 1 times f 5x plus 2 all over g squared. All right, so there's our derivative. We're going to want to simplify it. So I would just expand the top out. Notice that those 5x's cancel, and I get 8 over x plus 2 squared. And we can see that since x plus 2 squared is never negative, this derivative will never be negative. Therefore, the function never decreases. So that's the kind of argument that you need to make there. All right. I think that's all. So you can take a stab at this exit card. We'll take it up when you get to class. Find all points where that function has a horizontal tangent. And then the practice work below you can work on in class as well when I see you there.